This is slide number 20 and I am your presenter Asloob Mutassar. In the last slide we have presented this integral. So recall that this integral is actually the Fourier transform integral, and it gives the Fourier transform of the object function, which is small o of x comma y within the integrand, and on the left hand side we have the output, which is capital O of fx and comma fy. The x and y are the variables defined at the object plane, and the fx and fy are the variables defined at the back focal plane or the Fourier plane of the lens. In the figure you can see that the object O of x and y has been illuminated with a plane wave with a normal incidence. So when this plane wave passes through the small object O, it is disintegrated into small segments which each represents a plane wave going in different directions having different amplitudes, and these are received by the lens, and the lens integrates them at different points. And you can see that if you join the center of each plane segment to the center of the lens, you will reach at some dot points. These dot points in the black are actually the contribution of these segmented plane waves which were captured by the lens and focused at those points. And you can see that we have indicated there the Fourier variables fx and fy. These are this is actually the Fourier plane, or we can recall it as the back Fourier plane, and lens actually performs the double integration. So in this integral, if you recall that O of xy multiplied by its phase vector e to the power minus iota 2 pi within the bracket fx into x plus fy into fy is actually, this is the field just after the object O. And this double integration is performed by the lens. So that's why we have the total function, that is the integration of the integrand, and we get the total output at the back focal plane of the lens, which is represented by capital O. So capital O is actually the Fourier transform of this small o. So small o is the space variable in the space domain variable, and capital O is in the Fourier domain variable. So this field can be viewed as a superposition of plane waves of different amplitudes going in different directions. So here are some words that we have spoken earlier, that the biconvex lens performs the double integration. The output of a biconvex lens, which is capital O, as a function of fx and fy, is obtained at the back focal plane known as the spectral plane, spatial frequency plane, or simply the frequency plane, or more commonly the Fourier plane. Capital O of fx and fy is known as the spatial spectrum, or the Fourier spectrum, or the Fourier transform of small o of x and y. Symbolically, we can write them that capital O as a function of fx and fy is equal to the Fourier transform of small o, which is defined with the variables x and y. And you know that this is the integral that we have reproduced over here from our previous slide, but in addition we have shown the Fourier operator operating on the small variable o. So this Fourier operator operating on the small variable o, which means that we are talking about the integral on the right hand side of this one. So this is the Fourier operator on this one, and the output of this Fourier operator operating on the small o is on the left hand side, which is capital O, and defined at the Fourier transform variables fx and fy. So this operator is this operator, which is we call it as a Fourier operator, is shown at the bottom of the line. So the integral, remember that this integral is the Fourier transform integral, and we shall be using this integral again and again in our next few presentations. And this is the end of slide number 20.